So let's dive into plants now. So we have some theories about how the Cambrian explosion could have arisen, or we've questioned that a little bit. But now we want to talk about these early plants and how those developed. So we're going to start with our red algae. We have a fine specimen here of red algae. Here we are. And this, as you can tell, it has a robust calcium carbonate skeleton, if you will. So it has this is all calcium carbonate. And what it allows this organism to do is live in a high energy environment. So what high energy refers to is a lot of wave action, actually. And so if you have the development of this robust skeleton, you can withstand that wave action and persist in those kind of harsh environments. So the next early plant that we'd like to look at is the green algae. All right, ooh, a nice specimen there. All right, so green algae, so this is still calcium carbonate, and so you can identify the skeletons by these little delicate kind of leafy-like calcium carbonate precipitations. And so I mentioned that these are much more delicate. We got to be careful when handling this fossil, or this specimen here. And so what you can deduce from that information is that they actually have to live in a little bit more quiet, less energetic environments, such as a lagoon or kind of that back reef, back lagoon area. So, and why we kind of are interested in the green algae here is that these are thought to be a precursor to our land plants, which we'll get into in just a minute. Next is our brown algae. I know, algae's exciting, isn't it? Well, actually, I think brown algae is exciting because these are your large kelp, actually. So these are multicellular algae, and you get these huge kelp forests that I think are pretty fascinating. It's just algae and these huge structures here. So that's our brown algae. Next are our diatoms. So still, these are early plants. And these are algae that actually precipitate silica shells instead of these calcium carbonate skeletons. So diatoms actually have a silica shell. Boy, they're just beautiful, actually. And they have these really kind of geometric shapes. They're very symmetrical. They're gorgeous. They're gorgeous, these diatoms. And these actually comprise phytoplankton, actually. So I mentioned with the green algae that they may have been the precursors to land plants. So we want to consider what that would have taken, what the process would have been to transfer from the aquatic environment to the terrestrial environment for plants. So first of all, you would need a support system. The organisms would need support, and that's in the form of stems. So stems provide support in the land environment or the terrestrial environment, whereas in the water itself actually supports that organism. And so we kind of need that translation from water to land, and the first step is we need a support system. Secondly, roots allow for anchorage of that organism, and they also allow the uptake of water and nutrients. So roots are going to anchor that plant in position there. Next, we have the development of a waxy cuticle, so kind of a waxy surface there, or a covering of that plant, and that basically prevents too much water loss. So if you're on land in the terrestrial environment, you're exposed to air, and so you may have a little bit increased water loss, and that waxy cuticle prevents that process. Last, we have the development of vascular tissue. You have vascular tissue, and so do plants. And so do land plants, I should say. So vascular tissue allows the circulation of water and nutrients throughout the whole organism. So you have xylem and phloem. Sounds like a good name for a pair of fish or something, xylem and phloem. But the xylem tissue, so you can kind of think of these as like longitudinal tubes sort of running up the length of a plant. And so xylem allows for water transport and phloem allows for nutrient transport.